a thrill that, yeah, I've known Tina Neal for a long time, back to the eruption of Mount St. Helens in 1980. And she has always been a special person, and I'm so thrilled that she's carried on in her career. She will be, there are new developments in the USGS volcano world, and she's going to be recapping on a few recent eruptions. She'll also talk about USGS, that's the United States Geological Survey, Blossoming Diversity, Inclusion, Equity Push. As you can see, because she's now got the position, as she's either just started or soon will be as head of the volcano centers in the West, and we'll let her talk about that. She's a volcanologist with 37 years in hazard science, communications, mitigation, leadership, and she's worked for the USGS in the various aspects of volcanology since 1983. I know she's worked as head of the Hawaiian Volcano Observatory in Alaska, and she worked along at Mount St. Helens, and I'll hear more about all her details. We all will. She initially wanted to be an astronaut, but was introduced to volcanoes in college, looking at the Viking Orbiter of Mars. And the first earthly volcano was Mount St. Helens, where she did her master's thesis in Arizona. Then she worked at Hawaiian Volcano Observatory, HVO, in the early days of Pu'u'O'o's eruption. I always loved Pu'u'O'o because that was the volcano that erupted on the O on the some letter on the map there. So it wasn't a Hawaiian name, but it's cute. And she spent time in ALVIN expedition to the Rift system in the Galapagos, and she worked at the Alaska Volcano Observatory, AVO, where she participated in eruption response and related studies on several volcanoes. She has been involved in a lot of active volcanoes. In fact, people might actually be frightened when they see her because it's going to erupt. But let's hope that doesn't happen. She developed an interest in managing volcano hazard information and developing warning systems. And international work included collaborating with Russian colleagues on an eruption warning system in Kamchatka, and I can't pronounce this other one, but Sakhalin. Anyway, she'll correct me on that, as well as serving for the USGS Geoscience Advisor to USAID's Office of U.S. Foreign Disaster Assistance, supporting disaster mitigation and planning in countries around the world. She also presented the Volcano Hazards Program during the development of the USGS Hazards Mission Strategic Science Plan. So she's clearly had a lot of experience too in leadership, and like many volcanologists or scientists, at some point in your life, somebody knocks on the door and says, you've got to do leadership for a while. We need your expertise, because those people make excellent leaders. And she's clearly rounded the scale and can do a lot. And she returned to Hawaii and served as scientist in charge of HVO. And through 2020, managing the response to the destructive 2018 eruption. And she focused on hiring new generation of HVO scientists. That's always tricky, and that's really important. And planning new facilities and science initiatives, as well as preparing for the Mauna Loa eruption. Then she returned to AVO, Alaska Volcano Observatory, in June 2020, and was selected as the director of the Volcano Science Center in May 2021. So here we go. I'm going to pass it over to her and introduce Christina Neal, and thank you very much for giving a talk, and go for it.
Thank you, Mindy. Thank you very much. What a nice introduction and recap. I think it's so fitting that you are leading this meeting, because you're right. We first met around Mount St. Helens just a few years after 1980, and that was kind of the beginning of my career. So how fun it is, oh gosh, 38 years later now, to be sitting with you in this new format, which we couldn't even have conceived of in 1982. But it's great to see some other people on here that I know. Jody Bourgeois and I have been colleagues and friends for a long time. And I see Liz Westby from the Cascade Volcano Observatory on here. Anyway, nice to virtually meet all of you, and thanks for the time to speak today. So what I'd like to do is I'm going to talk a little bit about what it means to be the director of the Volcano Science Center, what the Volcano Science Center is within the U.S. Geological Survey, what our work is all about, a little bit of characteristic of our center and trends through time, some thoughts about what I think are some of the cool new things or developing things within the Volcano Science Center, and then show you some photographs and talk a little bit about some recent eruptive activity both in Hawaii and Alaska. And then I'll turn off the PowerPoint and talk a little bit about this topic of diversity, equity, inclusion, and accessibility that's really important for all of us right now. And then a few thoughts on what it's like to be, what I feel like it's been my experience being a woman in this career. And I hope there's plenty of time at the end to have discussion and questions. So I think with that, we will try sharing my screen and see if this works. Worked before, so should work again. Let me know if you start seeing slides. Whoops. How now? Does that look good?
Looks good.
All right. So I love this photograph. It was taken by a friend of mine in Hawaii last winter, this past winter, when the lava lake became active again at the summit of Kilauea volcano, Jill Briggs. And I just love this photograph showing the convergence of earthly process and the glow of the lava lake deep in Halemaumau crater with the Milky Way and shooting star above. Just a spectacular image. So what's happening at the U.S. Geological Survey's Volcano Science Center? And these really are my perspectives, being in the job since early May and still feeling like I'm learning a lot and drinking from the proverbial fire hose. So the mission of the Volcano Science Center within the U.S. Geological Survey is stated here. It's to enhance public safety and minimize disruption from volcanic unrest and eruption. And we do this by delivering effective forecasts and warnings to those at risk, as well as information about volcano hazards based on scientific understanding of volcanic processes. So as you can see from that mission statement, it's really a blend of fundamental scientific research into how volcanoes work and how hazardous processes impact the surface of the earth and people and infrastructure. And then also a very strong operational component by tracking activity at volcanoes and interpreting the information to be able to give warnings to keep people safe. And I think that's one of the fun things about this part of the USGS is that we are this nice blend of research scientists who are answering questions that they want to pursue to understand the earth, and also folks who are perhaps more interested and focused on delivering that information in a helpful way. That integration of research and operations is really important. So we have about 170 permanent employees in the Volcano Science Center. These are permanent federal folks. We have many more, maybe 80, 100 more people who are volunteers or affiliates through universities or temporary employees. And all these folks are organized in our 5 volcano observatories and also the Volcano Disaster Assistance Program, which is a program co-funded by USAID and USGS to assist countries overseas in mitigating volcanic crises. Our volcano observatories, as shown in this map, are located in Alaska. The Cascade and Yellowstone observatories are co-located at Vancouver, Washington. That's where Liz Westby works. California Volcano Observatory used to be Menlo Park, and it's transitioning to Moffett Field. And then, of course, the oldest one, the Hawaiian Volcano Observatory, where I'm so happy to have spent a part of my career. Also on this map, you might notice some other areas, the Commonwealth of the Northern Mariana Islands and the Western Pacific. This is an American protectorate that has active volcanoes, and we are responsible for tracking activity there and issuing warnings. And then something that's really not started yet, but even the American Samoa Islands down in the South Pacific have fairly young volcanic systems that we actually don't know much about, but as soon as personnel and resources allow, we need to address a little more in a more detailed fashion so that we can be ahead of the curve in case any of them begin to wake up. So we have people scattered across the West, and we also have scientists who work with us in USGS offices in Flagstaff and even back in headquarters in Reston, Virginia. Our center has about a $23 million budget per year. And, you know, there are lots of incredible things about the center and the work that it does. And of course, now that I'm directing it, I'm thinking more about the problems than the positive things, trying to get ahead of them. But some of the challenges we worry about, or I worry about, is that we have in the United States alone 160 volcanoes to think about. These are potentially active volcanoes across the landscape. And again, a big challenge for the directorship, I think, is trying to make sure the funding and the personnel resources continue to effectively blend basic science and research with this operational component of monitoring and warning so that we don't get out of balance. And as you can imagine, the operational part, the monitoring, putting instruments out on the volcanoes, looking at all of the data, keeping the instruments running, that tends to be a very expensive part of our operation. So this is a look back at the last 5 or so years, just at staffing within the Volcano Science Center. It illustrates we're growing slowly in terms of permanent staff, and that's a positive trajectory. There's no guarantee it will continue, but we hope it will, because of course there's always more work to do. And another trend through time, which may not surprise you, is that we're getting some different skill sets within the center. As our work becomes more IT and computer science intensive, we're tending to hire more people with those kinds of skills: data scientists, visualization specialists, computer scientists, to help with database development and just basically data management and processing to enable volcanologists to interpret information quickly. But still, the classic disciplines of geology, geophysics, geochemistry, and also communication skills are really critical. So it's a big part of my job to look forward and think about the workforce blend going into the future. And I would say, thankfully, we are becoming increasingly diverse through time. And I compare what is the center now with where it was when I started in the early 80s. You know, it's a very different profile, which is not to say we don't have more work to do. We're still largely white. We are still, not quite 50-50 in terms of gender. And so there's absolutely work to continue to do in that realm. So now I'd like to just walk through a couple of what I think are some of the exciting capacities and developments in the center. And some of this information I presented at the AGU meeting last December in a talk I gave with my fellow scientists in charge. But of course, in a very technology intensive field, it's always exciting to see what new tools are coming online to help us track activity at volcanoes and conduct research. And two that come to mind are of course, unoccupied aerial systems, or drones. We, in the fall of 19, before the pandemic, we were able to train up a bunch of pilots in Hawaii, and here they are practicing with a drone. Drones became a tool during the 2018 eruption for us in Hawaii. It was the first time in the United States, anyway, that USGS folks had used drones successfully in an eruption response. And the data collected, the imagery data, the gas data, were just fantastic and are supporting a ton of ongoing research. And so it's very clear that this is a tool that will remain in our kit and only grow as sensors continue to become miniaturized and lightweight, and we find more uses for drones. Unfortunately, right now we're in a bit of a holding pattern, partly because of the pandemic, partly because, unfortunately, a lot of the drones have Chinese-made parts, which of course have brought some security concerns into the mix. So we're in a little bit of a plateau in terms of application, but I'm confident that'll turn around. And then another really important tool, which isn't necessarily a new tool, but we're finding new ways to apply these to volcanoes, is infrasound, and basically looking at sound waves that travel through the atmosphere from explosions or mass flowage events or other processes. These are arrays of sensors that we can put hundreds, if not thousands of miles away from volcanoes and triangulate back to detect events and characterize events. And so what this tool is allowing us to do is not necessarily need to be right on top of a volcano with a bunch of instruments, but basically track things from far away and I think is opening up lots of new ways for us to efficiently and perhaps in a more cost-effective way monitor very distant volcanoes, such as in the Western Aleutians. We're also seeing lots of advances in our ability to alarm data streams. And what I mean by that is we're collecting data from seismometers and GPS and satellites 24/7, but people aren't staring at the screens looking at these data. Obviously, that's just untenable. However, using computer science and in the future, machine learning kinds of techniques, we are developing alarms to be watching the data automatically for us and then raise an alarm and call the volcanologist or send an email or a text or something when the data streams show a perturbation that may be of significance. And this was a really rich area for continued development because, again, we don't want people staring at screens 24/7. And as we develop more and more monitoring tools, the volume and the pace of data that are coming into our observatories is just exploding. So we're going to need machine learning techniques to help us process and track the data and let us know when things are looking like change is about to happen. The other potential, or the other real value in alarming systems and machine learning is that it allows us to work across the geography. In other words, during 2018, we had scientists on the mainland and in Alaska watching the data coming in from Hawaii because Hawaii scientists were busy. And so we're always looking for ways to make the observatories really interoperable and be able to back each other up, especially in crisis times. Another really important area for work, and this involves a lot of geoscientists with mathematical and computational skills, is developing physics-based models. These are models that can describe how ash will flow in the atmosphere, how lava will flow across the terrain, or how lahars will go down drainages. And these models, as they get more sophisticated, allow us to provide really much better information to emergency managers when an event either is about to happen or is going to happen, to help prepare for the kinds of hazards that their communities and infrastructure need to prepare for. So that's an area of quite a bit of focus. And then this last one is quite interesting. So having been through a number of eruption responses, I can tell you that there's always a cadence of, you see the volcano become restless, and there's a lot of discussion about what is going to happen next. And event trees are a way that we can use kind of a logic train of invoking what the volcano has done in the past, what analog volcanoes have done around the world when they become restless, to help us constrain the uncertainties of what outcome is most likely. And of course, this is of paramount interest to emergency managers because that's the question they're always asking us: what's going to happen next? So I see application of a lot of statistical approaches and access to databases with a lot of information about past eruptions, informing our use of these event trees or scenario based discussions to help come up with the most likely scenario for when a volcano becomes restless. So some interesting developments that I like to say are catalysts for this kind of progress and where we are today. Of course, our various sensors are getting smaller and cheaper, lightweight so they can go on drones, but also just smaller and cheaper to be walked around the landscape. Like this picture here shows a nodal seismometer about the size of a boot that can be deployed. You can put hundreds of these things across a volcano or a geothermal area and collect incredibly dense data sets in short periods of time and do things like this little animation, which shows a changing tremor source with depth in Yellowstone at Old Faithful. So these are the kinds of new subsurface imaging techniques that can be applied to give us a better understanding of plumbing systems of volcanoes. Also, we're dealing with both a blessing and a curse of this proliferation of satellite platforms. There are so many new eyes in the sky collecting data all across the electromagnetic spectrum. And one of the challenges we have is high grading the information from these satellites that will help us monitor volcanoes and their status, detect eruptions, and track ash clouds. So we're working with NOAA and NASA and other partners to get the pipeline from their satellite acquisition systems to us to support our mission. And this is going to be a big data management challenge going into the future. Other catalysts for progress, every time there's an eruption or an unrest sequence, we learn a lot. We learn a lot about a particular volcano and how it behaves. but we also learn what our monitoring data streams mean. And so recently we've had some great examples in Kilauea, of course, 2018, that went on for 3 months, and the Bogoslov eruption in Alaska, 2016 and 17, which was this fascinating sea level explosive eruption in the central Aleutians. Both of these eruptions have just given us gigabytes and terabytes of data to dig through, and I think are resulting in quantum leaps in our understanding of volcanic process. And we've also been fortunate since 2000, mid-2000s, to receive some tranches of money that come in through various federal actions, such as the American Recovery and Rescue and Recovery Act in 2008, which delivered some funding to USGS, and we applied that to upgrading a lot of our systems. And then through time, we've been getting some other buckets of money for very topical applications, such as a lahar warning system at Mount Rainier. So these infusions of cash have allowed us to make fundamental investments in upgrading our systems and focusing on particular hazard scenarios, such as the terrible mud flow hazard at Rainier. So in kind of looking ahead at what I expect to be coming down the pipeline, we are going to be able to deliver better forecasts in the coming years. And part of this is because we have continuously improving monitoring networks as funding allows. We have these physics-based models and improved system understanding. So as an example, on the right, this is a lava flow propagation model that was generated by Hannah Dietrich of USGS during the 2018 eruption. And it's not, I mean, it's a sophisticated computational model, but it's really using the fundamental physics of what happens when things flow downhill. And the output is very useful to emergency managers because they can instantly look at this and see from the color density what areas are at greatest risk. So this kind of a tool and other tools, similar tools for lahars and ash cloud propagation in the atmosphere, the dispersion of volcanic gas clouds, these are becoming more turnkey during crises to support emergency response. Other things I think that are coming is that our approach to doing hazard assessments for an individual volcano are being modernized. We want to make these things more dynamic so that they respond to changes in the state of the volcano, and incorporate lots of updated geologic insight into histories of volcanoes as we gain that, and trying to make these hazard assessment products more useful to our stakeholders rather than just a static map on the wall. We want to give people information that allows them to make the right decisions about long-term planning and emergency response. The other thing, of course, through time is that our messaging and our ways of communicating with stakeholders change all the time. Now we have Facebook and Twitter, and who knows what we're going to have tomorrow and next year. And we have to use these platforms efficiently and carefully to make sure that our messages are getting out, that people are understanding what they need to. And we're trying increasingly to use insights from social science to inform how we do this, because other agencies like the Weather Service have spent a lot of time studying how people hear warnings and if they make the right decisions and understand exactly what the potential impacts are. So we're trying to learn from partners on that score. It's also really important that we move faster on disseminating data, not just to the public, but to our academic colleagues. There's a tremendous appetite for seeing the raw data and the first order process data quickly. So there's an obligation as a federal agency, of course, to do that. And then also we'll continue to work on community preparedness issues. And of course, that's where the rubber meets the road to help people be safe on the landscape, is identifying the hazard and then working with community leaders and community members so that they have emergency evacuation plans that are proper and know what they're facing. And I think given the emphasis right now in the world on DEI kinds of things, we're also going to be targeting, thinking about our services to underserved communities. So these would be communities that don't speak English, communities that are kind of on the edge of economic solvency and are worrying about many other things besides volcanoes. So we need to be thinking about how we communicate to them. In terms of our science and technology, I think one of the things we'd like to do is for every high threat and very high threat volcano in the United States, really work on developing a conceptual model for how they're plumbed. What do they look like underground? How does magma accumulate? prepare for eruption, and then erupt. Right now we have cartoons like the one on the right here for Kilauea, and we have new techniques in geophysics and petrology to really refine these cartoons to help us understand the dynamics of magma structural interactions, and this will only better inform our ability to issue forecasts when unrest occurs. I've already mentioned this kind of routine use of new technologies, including drones and new satellites. As we expand our monitoring networks, I'm a big proponent, and I'm sure hopeful that out there's some new battery technology that will save us from having to helicopter in hundreds and hundreds of pounds of batteries for every monitoring station on the volcano. It's carbon intensive, it's expensive, and it creates a waste stream that I hope we can get away from in future battery technology. Already talked a little bit about improved alarm systems and the use of machine learning and artificial intelligence and the cloud for advanced computational needs. So those are things that I think are definitely going to be priorities coming down the line. Another thing that might be of interest to this group is that we've tended to focus on what I call the charismatic volcanoes, the stratocones and the Cascades in Alaska, and then of course the big shield volcanoes in Hawaii. But we've not spent as much time thinking about this distributed volcanism in the American Southwest, these small basaltic fields that are in Utah, Nevada, Arizona, and even Eastern California and Oregon. And so there's an effort underway to try to focus more of our attention scientifically and in terms of monitoring on those volcanic centers. And this will have to be done in partnership with a lot of universities. We just don't have the bandwidth to do all this. One could make the argument that for the American mainland, where is the most likely next eruption, maybe other than Mount St. Helens, going to be? And it may well be a basaltic cinder cone in the American Southwest. So I don't think those folks who've got their minds all wrapped around wildfires at the moment are really thinking about this, but we need to start that conversation. And then I put this one in for Jody. During my time in this job, I think an effort of mine is going to be to strengthen our work with the other USGS hazard programs, which already have very strong connections to us, but the landslide and earthquake programs in particular, because we share lots of goals and techniques, and particularly in terms of instrumentation in the field. And on the right is a cover page from a open file report that was just released. Jody, you might be interested in this. This is about a landslide that's been observed in Prince William Sound, a slowly creeping landslide that if it lets loose is going to create a big wave that will impact Prince William Sound communities. And the Volcano Science Center folks are working with the landslide folks as well as the state geologists in Alaska to instrument the area to try to monitor this landslide. So there's a lot of crossovers with our colleagues in other parts of USGS. A couple comments about our sort of observatory operations, I think important looking forward. One is we want to become increasingly interoperable. That's kind of the buzzword of the day, such that our observatories can back each other up, as I described. And that involves a lot of technology, just developing a lot of new procedures and thinking about protocols for data monitoring and watching and archiving. And this is increasing virtual environment. This makes a lot of sense. And who knows where we're going to be after the pandemic is over. We're working towards using more common software and hardware. That's just a plain efficiency goal. And another really important thing is we're trying to become a little bit more structured in our event response. For those of you who've had any incident command response training or national incident management system training, these are concepts of more structured and organized crisis response that we really have not yet ever applied in an actual volcanic event. And I'll show a picture in a minute of what I mean. I think going into the future, our collaborations with academia and other agencies will only become more important. And as I keep coming to this notion of increasing staff diversity, this is definitely on that trajectory and will continue into the future. So here's what I wanted to mention about what might the next eruption look like in the United States. And don't worry about mastering all the box labels, but this is what an incident command system approach to a volcanic eruption response would look like, where all the different jobs during an eruption, such as a hazard forecasting lead or the public information officer or the monitoring system lead, will be determined ahead of time, and people will actually live, quote unquote, live in those boxes the idea here is just to make sure that everything is attended to and you're not forgetting anything. FEMA and wildfire response, they love this kind of thing because it's very organized and efficient. It's a little bit of an anathema for the scientific community to think this way, because we don't like to be so prescribed and organized. But I think we recognize that, especially in a major crisis, like an awakening of a cascade or a volcano, or heaven forbid, Yellowstone waking up, it's going to be all hands on deck, and there's going to be so much demand for performance and delivery of data and interaction with other agencies and those at risk that we are going to have to be very organized. So we've got a plan. That should make you all feel comfortable, right? We've got a plan, and this is the plan, and we're going to be practicing it in the coming years. So of course, there are lots of wild cards out there, and these are things that we think about informing our planning. And of course, obviously, societal vulnerability is only going up as more people live in volcanically vulnerable areas, and indeed in areas that are subject to hazards from multiple phenomena, coastal flooding, as the climate changes. Who knows what the pandemic and post-pandemic workforce and workplace constraints will add to our challenges. But I'm trying to look at these as opportunities to do things differently and perhaps better. And then, of course, there's the funding uncertainty for us. Like all federal agencies, we sort of oscillate up and down with the funding cycles. We're fortunate right now to be in a science positive administration, and I think right now things are looking good. These instrumentation packages that we put on our volcanoes, they're mostly on federal lands and often in wilderness areas. And of course, you understand that takes a permitting process that can be protracted and sensitive. So that's a challenge out there for us, and something that we will work through carefully and of course legally and pay good attention to. And the other wild card and external force that I always remember is within the context of climate change and climate science becoming so important for all of us. I think we need to look for ways, or I'm trying to look for ways, that our work can dovetail or support or be influenced by a focus on climate science. And for instance, we have hundreds and hundreds of these monitoring sites all over the Aleutians and the high Cascades. Could we be combining efforts with climate scientists to be collecting meteorologic data or weather data that is of use in further climate models going forward? Okay, well, that's all the management stuff I'd like to share, just perspectives from what I'm trying to do day to day in this job. And now let me walk through a couple of recent volcanic events in the US. First is my personal favorite, Kilauea volcano, of course. And this was after the 2018 eruption ended in late summer of 2018. The volcano went into a very quiet phase. At the summit of the volcano that had collapsed many hundred meters during the 2018.
I meant
the deep Halemaumau pit crater began collecting water in August of 2019. And this is a shot looking down into the Halemaumau crater at the water lake, which had grown to a depth of about 50 meters by late 2020. Well, the night before solstice, an eruption began in the wall of the crater and beneath this water lake. And here it is, 12 hours into the event. That water lake was boiled away rather quickly, and in its place became this beautiful lava lake starting to fill up Halemaumau. And here's a photograph taken a week later, showing the lake has grown and widened as it's filling in the bottom of Halemaumau, the beautiful cooled plates of lava forming those black crustal plates on the surface. The eruption went on into July, and by its end, it was more than 200 meters deep. The volcano has returned to being quiet, but it was a very photogenic eruption, and it was very well timed because we had just hired a whole bunch of new geologists at HVO. And this was a great first eruption for them to get their feet wet in both the nuances of eruption response and crisis management, but also how to approach an eruption and glean scientific information. So currently the lava lake is quiet. There's no surface activity. Of course, it's still molten below the crust and will be for many years. Here's a HVO geologist using a laser rangefinder to measure the distance to the lake. And this was one of the tools that they used to track the depth of the lake through time. That upper plot shows the depth of the lava lake from when it began in late December through early July. You can see it really grew quickly and then slowed down in terms of its depth as the funnel-shaped crater was filled after about February. In the end, first they were making optical measurements daily, I believe, or maybe even multiple times a day. And then they transitioned to using a laser rangefinder that was an automated distance measurement device to track the depth. HVO also is still concerned about Mauna Loa volcano, the big volcano right next to Kilauea. And this was a volcano I spent a lot of my waking hours thinking about when I was at HVO, thinking about the next eruption. It hasn't erupted since 1984. And it's historic, or I should say last few hundred years of recurrence interval is closer to 7 years. So one could say we're kind of overdue if that recurrence interval is real. But the volcano has been in an inflationary mode, meaning it's accumulating magma in its shallow system since about 2014. And just this last spring, it went through an additional inflationary spurt. This upper plot shows the distance across the summit caldera of Mauna Loa, and during an extension period, it was inflating. That shows a change of on the order of, I think, 1.5 centimeters across the caldera. And then it went through a very rapid contraction, which was so interesting, and coincident with a burst in earthquakes located below the volcano shown in the lower plot. I think the HVO staff at this time thought something might be getting ready to really move towards eruption, but then it just quieted right back down. And since early April, it's been really pretty quiet. So it's clear we don't know exactly when Mauna Loa will next erupt, but it will erupt again. And this is one we're watching very carefully because of its potential impact on people on the Big Island. For those of you who've been there, you know that eruptions, especially from the southwestern rift zone, can move very quickly downhill and even cut the only road around the island just within hours. So it's very important that HVO detect the earliest signs of unrest at this volcano, get people prepared, and then as soon as an eruption begins, the big challenge is going to be detecting which way the lava is flowing, and that will inform what civil defense's reaction is. So lots of effort going into planning for the eventual Mauna Loa eruption. Although I just want to emphasize, in case anyone is listening out there, it's not showing any signs of imminent eruption now, so people shouldn't be too concerned. So in Alaska, where I'm currently living, this is always a busy place for eruptions with so many volcanoes. I forget the current count. It used to be 52 historically active volcanoes. That was easy to remember because it was a card deck, but I think they've added some. Right now, there are 1, 2, 3, 4, 5 volcanoes either restless or actively erupting. And that's a little bit above average for the Alaska Volcano Observatory, but here's some pictures of a couple of them. Semi-Sopochnoi volcano out in the western Aleutians. Jody, I think in Russian that means 7 hills, if I'm not mistaken. This volcano sprang to life in April with a lovely ash plume detected on satellite imagery there on the left. It's not a very tall ash column. It probably only went up 5,000 or 6,000 feet, drifting downwind. Unfortunately, nobody's living out there, and air traffic is sparse. Our field crews were out there later in the summer doing work, and so on the right is a photograph of a continuing ash emission from an intracaldera cone at Semi-Sopochnoi volcano. Pretty typical activity for the Aleutians. Another volcano that's in Alaska that's frequently active is Cleveland volcano in the central Aleutians, and here's a great next view satellite image looking right down the throat of the volcano, showing a beautiful little lava flow that came out in August of this summer. This is the kind of thing that probably even 5 or 10 years ago we would never have seen. We just didn't have the satellite data with frequency and resolution enough to be spotting these kinds of things, and nor did we have instruments that far out in the Aleutians to detect earthquakes or other signs of activity. So it's pretty remarkable right now, the volume of information we're receiving, and frankly, it makes it look like there's a lot more volcanic activity, but I think we're just much better at detecting it. And then here's Great Sitkin Volcano, another Western Aleutian volcano right across the strait from ADAC, which used to be a big military installation and still is an active community out there. This photograph was captured by a fish and wildlife biologist on their research vessel in the evening of the May 25th. And our geologists were soon there on another mission, but flew out to Great Sitkin and collected the juvenile bomb that you see in the lower right. This volcano has kind of gone back to sleep since this one burst. And I shouldn't say completely back to sleep. We're still seeing some earthquake activity, so this eruption may not be over. And then it's not just eruptions that we have to deal with and think about and respond to. We have many episodes where a volcano shows signs of unrest, strong earthquakes or deformation, or even increases in gas, and then it goes right back to sleep, or the unrest may not even be related to the magmatic system. Still, because we're detecting these things and people see the activity, we have to respond and tell the public what our assessment is, and certainly tell emergency managers. So this is an example from Mount Hood in June of this summer. An earthquake swarm, which is typical of swarms that we've seen there for many years, happened sort of off the volcano, associated with a regional fault system. And we had to put out information just saying, we see this at this point. It's not a volcanic concern, but of course we're watching it. So another example of the kind of work that we have to do that may not be related to an actual eruption, but still unrest that people are concerned about. And I think that is where I'm going to end my slides. And I'll unshare. Now, do you see me instead of my slides?
Yep, that's great.
Okay. Well, I'm happy to answer questions if people want to stop at that point, Mindy, or do you want me to just keep going about diversity and history?
Why don't we just answer a few of the questions, and then if you wouldn't mind, go on about diversity and some of those others. Now, we have some questions already, and people may have some. I know, let's see.
Okay, I can see the chat. So I'll go back up to the first one, the COVID response. Well, yes, let's see, how to answer that. You know, I will say that in my experience, delivering information about volcano status through our formal channels. So for instance, we have a notification system where we put out messages by email, and go to our website, you can sign up for the service. Or we have regular telephone phone calls with our partners. You know, we don't get a lot of pushback. I think